All right, ladies and gentlemen, for the next part of our electricity unit here, what we're going to be getting into is we're going to be getting into talking about circuits. All right, and there's two different types of circuits that we're going to be looking at. And we'll look at those two different types of circuits today. But before we even get into those types of circuits, we're going to need to understand three main concepts that are involved with circuits, and that is voltage, resistance, and current. Okay, those three concepts and how they relate to one another is going to be very important to understanding circuits, and eventually you're going to be able to calculate all three of those within any given circuit. So we'll start off just talking about voltage. All right, voltage is sometimes called electrical potential, is another name for it. So if you ever see electrical potential, that's another name for voltage. So as a variable, it is usually written as just a V. Sometimes, like on your equation sheet, you might see it as delta V. Don't get too hung up on that. All that's telling you is that's just a voltage difference or electrical potential difference. So we measure this in volts, and the way that our batteries work is it causes a chemical reaction to create that voltage difference between our positive end and our negative end of the battery. Okay, and then the higher the voltages, the greater a current within a circuit is going to be. Okay, um, so moving on to, we have current. Voltage is actually what makes something makes the electrons move within a circuit, and that movement of charges or movement of electrons is what we call current. All right, now the higher the electrical potential is, remember, electrical potential, just another word for voltage. So, or the higher the voltage, then the higher the charge per second is going to be, or the higher the current is going to be. Okay. The equation we have for current is I equals Q divided by T. All right. Now, I is what we measure, or is the letter that we use for current. And we measure that in something called, I'm sure you're all familiar with this, either amps or amperes, or you can just use the letter A if you're talking about a number. The other way that you can solve for it, or the other thing you can call it, is charges per second or charge per second. And the reason you can call it that is because of what we're taking right here. We're taking Q, which is charge. And remember, we measure charge in coulombs. And then we have T, which is obviously time, and we measure that in seconds. So when you take that equation, I equals Q divided by T, what you're really doing is you are taking coulombs divided by seconds, or coulombs per second, or charge per second. Okay, so we will typically use the word amps for measuring charge, though. All right, moving on to resistance. Taking a look at resistance, what resistance really is it is a measure of how much charge is being slowed down. Sorry, I had to pause the video there for a second. I had to go make sure I let my dog out. But we were talking about resistance here, and resistance is basically the something that is slowing down charge. It's a measurement of how much charge is being slowed down, or how much current is being slowed down within a given circuit. So it depends on the material. Within a given circuit, a material might have, different types of metal. A lot of good circuit boards use gold as a good material or a good conductor. is another word that's used, and we'll talk about the difference between a conductor and insulator when we start talking about series and parallel circuits more. Could be something like copper is another common one used. So the type of material used makes a difference in resistance. Cross-sectional area would be something like, that's why I have this straw example here. In a circuit, when you're using a wire, the wire has what is called difference in gauges. So you talk about different gauged wires. So if you have a really small wire, that's going to be a really small gauge wire, right? And the bigger the cross-sectional area of that wire is, right, the bigger the gauge of the wire is. And so the higher or the smaller the gauge of the wire is, the higher the resistance is going to be. So these ones would have a really high resistance, and over here the bigger gauge would have lower resistance, right? And I use a straw as an example because if you have a really small straw, like a coffee stir straw or something like that, you're going to have really high resistance, right? And if you can imagine trying to use a straw, use a really small coffee straw to drink whatever it is you're drinking, it's going to be a lot more difficult than if you were to use one of these bigger straws over here. The resistance would be a lot lower. We measure this in something called ohms, and we represent this with Greek letter omega. All right, so moving on to Ohm's law itself. Ohm's law, it's V equals IR. You might remember this from your freshman year of high school. In ninth grade physical science, we talked about V equals IR. But it says electric current is proportional to voltage and inversely proportional to resistance. So the way that I like to think about this is like in terms of batteries, right? If we take, so we're using V equals IR. And if I'm going to say that I have a 12-volt battery, and that is never going to change. All right, 12-volt battery, it's pretty common voltage size or battery size. If I have a 12-volt battery, and that's never going to change, if you increase or change the amount of resistance, that's going to change the amount of current within a system. So if I have, let's say my resistance is, I have 2 ohms of resistance. Well, what that means is I'm now going to have 6 amps of current. All right, I changed that resistance, and that's going to change the amount of current within the system. Remember, that 12 volts is going to stay the same, but now all of a sudden if I say, okay, let's increase the resistance, all right, that'd be like taking a smaller gauge wire, right? I increase the resistance, and now I have a resistance of 4 ohms. Well, now I'm going to have a current of only 3 amps. Okay, so we'd be losing current, or the flow of charge would be slowing down. All right, so that's kind of Ohm's law. I want to give just an analogy or another analogy. I like using this as an analogy just to kind of, really get into your heads what kind of how charges flow and how voltage, resistance, and current all relate to one another, because it's not something that we ever see, so it can be hard to kind of visualize. So how do these, I guess we won't use 3. I'm only going to show you one analogy here. So I have a water system analogy here. And if we think of water in the city of St. Michael going to your house, and we think of this whole thing as one giant circuit, all right? The water tower here would be like your battery, okay? And what does a battery do? Well, a battery provides voltage. Oops. All right. And that is like electrical pressure. Okay. So you can think of the water tower as providing, we know it provides water pressure. The way a water tower works is it has all this water sitting up here, and it's gravity fed in the downward direction, and it's creating all this pressure so that it can supply pressure into the pipes to give you water into your homes. All right, and that's why water towers are up so high, and they have water towers in a lot more flat areas because we can't get the water up high enough. If you ever go out somewhere like in, maybe Colorado or in Montana, somewhere where there's mountains or something like that, they don't need water towers out there because they can just put their water up higher somewhere. All right, so this water tower would be like the battery providing, in the sense that it provides water pressure, and that's exactly what a battery does. In when we're talking electrical systems, a battery provides, I think of it as electrical pressure. Okay, excuse my sloppy handwriting. Okay, so a battery provides electrical pressure. And going back to the water system analogy, that water pressure then is going to create a flow of fresh water that goes to your home. Okay, so this flow of water is representing our current. Okay, and go back to the electrical. That's exactly what a battery does. When we have that electrical pressure, that creates a flow of charge that we think of as electrical current that we measure in amps. Okay, now as far as resistance goes, the only way I can really show resistance within this analogy is if you take a look here, you see that we have over here where we have fresh water out, the pipe is much bigger. And then over here where it gets closer to your house, the pipes become much smaller. The resistance over here next to the water tower is going to be fairly low. Okay. You're not going to have, your resistance is going to be fairly low, and the current is going to be fairly high. Versus when you get over here, you're going to have your resistance is very high. That pipe is becoming a lot smaller. So your resistance is going to be a lot higher there. Okay, and then what ends up happening is you end up using water in something like maybe it's your shower, your toilet, your sink, something like that. Sorry if you hear dogs in the background, that is my puppy and my other dog playing. That's what I had to take care of. But anyway, when we, your shower, your toilet, or something like that is something that would be something that uses voltage, or in this case, it's using water. All right, and we call those kind of things resistors. So resistors are anything that use voltage in an electrical system. And it could be something like a light bulb. It could be something like your radio that you plug into a wall at your house. It could be a motor of some sorts. Literally anything that is slowing down the current of the circuit is going to be considered a resistor. All right, and then the final part of this would just be that once you use the water, it goes in the sewer pipe, goes back out into the world, and then eventually at some point, due to our water cycle, it will end up coming back to you. Not saying that you are using sewage, but eventually it gets cleaned somehow and comes back to you, right? All right, so moving on to some circuit diagrams, which is what we're going to focus more on tomorrow. I just want to introduce circuit diagrams, the very basics of circuit diagrams before we really dive into it tomorrow. As you'll see on this slide, we have a bunch of different kinds of symbols that represent different things within a circuit diagram. What a circuit diagram is it's really just a simple way for someone like an electrical engineer or maybe an electrician to look at a picture of a wiring or what's going on within a wiring system. So a straight line would just be a wire. If you ever see something like one of these are switches. One of them is an open switch, one is a closed switch. Here we have batteries. These are types of batteries. If you ever see something like that, like a short line and a long line. An ammeter, circle with an A, is something that measures current, and I'll show you how we measure those with a ammeter or a multimeter. A voltmeter measures voltage. A light bulb, or sometimes you might have a light bulb where it's literally just it's a circle and then maybe it looks like an actual light bulb in the middle. And then you have a resistor, and this resistor here could just be anything, just slowing down the current. And I use this symbol a lot when I'm using my circuit diagrams. Okay, so looking at our two types of circuits that we'll be dealing with. The first type is a series circuit. All right, this is the most simple kind of circuit that you can have. And in order for it to be a circuit, it has to be completely closed off, or it has to have a complete path for the charge to flow. So we have a battery over here, and then we have resistors 1, 2, and 3. All right, the current is just flowing in one direction, and it just keeps going over and over and over again. It's got one path to flow. The other type is parallel circuits, and this is where we have multiple paths for electricity to flow. Oops, let's see. So here we have the circuit is able to flow through multiple paths here. So when it hits one of these branches or one of these parallels, and the reason we call it parallel is because all three of these branches are, well, parallel with each other. When it hits these, the advantage to this is that every single one of these resistors now, resistor 1, 2, and 3, are all going to receive the same voltage. And that's kind of one of the advantages of using a parallel circuit. And that's why we use parallel in our homes instead of using series circuits as well. Okay, and like I said, we're just kind of briefly introducing these, and we will get more into these tomorrow. We'll get more into depth on series versus parallel and kind of how to calculate some voltage, current, and resistances with those as well. All right, and the last thing I want to talk about today is using a multimeter within a series and a parallel circuit, or just using in any circuit in general. We're not going to actually get to use a multimeter, but I think it's good information to know in case you ever need to use one in your lifetime. So when you're using a multimeter, now keep in mind that a multimeter is something that the reason we call it a multimeter is because it can measure multiple things. Before we had the terms ammeter and voltmeter, and those are specific to just measuring one thing. Ammeter measures current, voltmeter measures voltage. But when we're talking about a multimeter, that can measure voltage, that can measure resistance, that can measure current. So if you ever want to measure, if you ever were going to measure voltage drop across a light bulb, all you have to do, or doesn't have to be a light bulb, could be any kind of resistor. If you want to figure out how many volts something is using, you're going to put each lead, and that's what these things are called, lead or terminal, the positive and negative, on either side of your resistor. And you just have to make sure you have it set to the voltage setting, and then it would give you the amount of volts that that object is, or that resistor is using. And then if you ever want to measure the current flowing through a system and you have a multimeter, you just change your setting to measure current. And then instead of having your leads on either side of the light bulb or resistor, now you're actually just going to create a series circuit so that the multimeter is completing the circuit basically. So what you want is you want to have that multimeter so that the current has to flow through the multimeter. That's the only way that it can actually read it. Okay. I think the last slide is just kind of a Yeah, just one final picture. Just once again, series versus parallel circuit. So tomorrow we will go more in depth on series versus parallel. We'll have a couple questions on your exit ticket that are just kind of some conceptual questions. Let me know if you have any questions. Have a great day.